In this slide, we'll introduce the DFT synthesis equation. So DFT basically converts the time representation. So x is a time representation. So typically we say x of n, and then we are given a vector, and each of these elements is a vector representing the sequence x in time. And n goes this way. N equals to 0 to n minus 1 for the last term, and therefore x belongs to Rn. A vector of n elements. Okay, so this x is representing a vector. I mean, if you want to refer to the back, then it was the y that we are talking about here. But now I would like to introduce you to the notations typically used in most books for DFT. So x is the vector in time, the vector of interest, and we can construct x by the Fourier basis. So this is the Fourier basis. Later on we'll see what is this, where x is the Fourier coefficients. So this big X here is representing these CJs here. Now, in the DFT literature, the small x represents time, and the same x, but now in capital, represents the frequency coefficients. Okay, so let's see what the DFT synthesis equation does for us. Basically, DFT synthesis means to construct, represents the signal of interest in time as a sum of scaled phase-shifted orthogonal complement exponential vectors. So I'm going to tell you, I color-coded it. The green represents the sequence in time. The blue represents the coefficients, the DFT coefficients, and the yellow represents the Fourier basis, the orthogonal complex exponential vectors. So this is the typical equations that one will give you in a book. So the green vector, time. The yellow vector, the yellow is the Fourier basis. The blue is the DFT coefficients. How do you interpret? X of little n here is the time index. Time as in discrete time. From 0 to n minus 1, because we are dealing with finite dimensional vector of length n. And remember, we start with index 0, so you end in n minus 1. The blue represents the DFT coefficients, and also the k goes from 0 to n minus 1. Now, x of n typically is Rn, meaning that all elements is real. X of k belongs to Cn because each element is a complex number. Now, what about the W's? Later on, you'll see that the W is a matrix. So this big thing is the W matrix. This vector here is xk from k equals to 0 to n minus 1. So capital X0, x1 until n minus 1. What about xn? So this is small x0, small x1 until small xn minus 1. So you realize that actually the DFT, the inverse DFT equation here represents x as the DFT coefficients scaling this IDFT matrix called WH. There's a 1 over n here, so don't forget about this. And this is actually we can think of it as the orthogonal decomposition, basically because you are decomposing this vector as scaled version of these columns multiplied by these entries over here, which is matrix vector multiplication. Now, let's study carefully what Wn minus Kn means. Wn here, this n is the number of elements in xn and xk. So we use the big N to denote how many dimensions we are talking about. This minus Kn here is this. There's a Kn here. So where's the minus sign? The minus sign is introduced twice here, so it becomes plus. Okay, so later on you will see what we're talking about. So this Kn represents this Kn. So it is a complex exponential of amplitude 1 with this frequency together. Okay? Now, when we fill up this matrix, we are filling it up in this way. Along the, what do you call it? As we go down, along the rows, remember on the left hand side we have a vector going from x0, x1, x2. So this is along time, discrete time. So here we are also talking about discrete time here, a long time going down. And what about on the right hand side? The k's, the x of these are indexing k's. And since k go from 0 to 1, so therefore we are also viewing this matrix from the horizontal directions as along k's. And later on you'll realize that the word k is for discrete frequency, the harmonic, the kth harmonic, we use the term. And the first column is the kth equals to 0. The second column is k equals to 1 and until k equals to n minus 1. Okay, so now we have this DFT and synthesis representation. Let's just memorize this first, and now let's repeat what we understand. In the synthesis equation, we are representing the time vector as linear combinations of the Fourier basis. The Fourier basis is this guy, which are complex exponential vectors, and they are being scaled by the big X, which represents how we can scale each of these columns by. And since these guys, the basis vectors, are orthogonal to each other, our understanding is exactly the same as Theorem 5 here. So, let's finish the description. Why do we need 1 over n? The reason why we need 1 over n is because we are going to introduce the W matrix. We have just introduced the WH matrix, and the WH matrix is a matrix, the inverse DFT matrix, and W and WH, when they multiply together, they are orthogonal, but their norm is n. So we need the 1 over n to remove or to denormalize this such that we get I here. I'll give you an example. What is the first column, all the ones, inner producting with all the ones? And you realize that if there are n elements of them, you'll get n here. So this column, when we are performing inner product to itself, will get n. The second column, when we are inner producting with himself, will also get n. So that's why we need to divide it by 1 over n, such that WH and W will get a matrix that is n in the diagonal. And then to make it identity, we are dividing by 1 over n here. So this is the reason that we are introducing this scaling. So I haven't tell you what is W yet, but if I've introduced WH into this form, the answer of W will become clear. W is the complex conjugate of WH. I should say complex conjugate transpose of WH is conjugate transpose of W. So with that, let's proceed.